ITE is a powerful AI-based application using recurrent neural network technology. It is available on the SAP Application Center and supports water distributors in detecting loss predictively, both commercial loss as well as technical loss in the pipelines and distribution system to ensure increased revenue and minimization of loss against what we would call an economic level of loss. The loss level that is as low as possible without costing more to fix than it is costing in spent water. The solution uses information from your network as it exists today, including currently available pressure gauges, sensors, meters, and, of course, third-party, publicly available data and other proprietary information. We have out-of-the-box leakage component-level leakage models for each type of pipeline, including ductile iron, traditional cast iron, steel-based, reinforced concrete, and the type K copper piping that often enables many local network connections. Adding this to field surveys and aerial data that is used to profile illegal or otherwise undocumented connections to the network topology allows us to forecast leaks, to identify pipeline level leakage, to establish a model for each type and each component of pipeline in the system, and to show where the losses are predicted to be greatest, where the effort needs to be focused on fixing, and performing either a repair speed reduction, a active leakage management, infrastructure replacement, or pressure reduction solution with the addition of pressure reduction valves. Let us look at an example. In this case, we are monitoring for a number of different metrics. Apparent loss, which is your commercial losses at the level of an individual connection, where water usage against expected consumption profiles is tracked. Real loss, which corresponds to water loss through leakage in the pipelines. The UARL, which is the unavoidable rate of loss. The CARL, which is the current annualized rate of loss. And the infrastructure leakage index, which provides a view of which components in the infrastructure are causing challenges. We also track against other information, such as weather-based disruptions, soil and groundwater conditions, special events, and other issues that may be affecting the performance of specific components, including storage tanks, distribution class 2 piping, transmission mains, ductile iron piping, steel piping, and concrete reinforced piping. What this allows us to do is to control for a number of different factors, including specific issues that affect consumption, that affect the rate of leakage, and that affect the pressure that is identified at different points in the network. We use all of this information, including a prediction of exactly how much pressure should be recorded versus what is actually observed at different points in the network, the water usage that is expected versus what is actually recorded on a particular meter, and, most importantly, component level leakage models that give us a view of exactly what the economic level of leakage, or the level that should be permissible, given that it is too expensive to fix the component further than that level, is for each particular type of piping. In this case, we see that we have identified within the network several components: class 2 piping, both steel and ductile iron, where there is losses that are predicted significantly above the economic level of loss. In other words, where there is loss that is substantially more expensive than the cost of fixing it would entail. We can see which specific components those are and make them isolatable and identifiable through our solution. Let's take a look at what those components might be. We have our mapping graphic here, which focuses on the storage tank and gives you a good view of exactly what the water flows look like. The water flows marked in blue correspond to the areas of greatest loss. In fact, where the loss level above the economic level of loss, right, is greater than 22%. We also are tracking for the types of events, including pressure spikes that require a pressure reduction valve, or temperature-related expansions and contractions that may be affecting the performance of steel-based pipes. What we are able to do is to profile the expected versus observed pressure and the expected versus observed flow, including consumption at the meter level at the end of a connection, and pressure within a piece of piping, to identify two key areas. One, ductile iron piping to temporary storage unit 192, and the steel-based piping to temporary storage unit 109. These two may be identified on our diagram quite easily. We can see here that this connection is marked in blue, where the water is going to an intermediate storage unit or a temporary storage unit. And, moreover, where the steel-based piping is causing another challenge that is marked in blue, and where the ductile iron connection from the storage tank to a distribution substation is also marked in blue. We can see that we can manipulate this diagram and isolate the specific parts to visualize and profile the flows that are causing the greatest leaks. Moreover, we can see that when compared against the unavoidable rate of loss and what is considered the economic level of loss, where you have losses that are not as expensive as the cost of repairing them, we are significantly above them for both of these situations, which are related. The temperature-induced contraction has caused warping and leakage, resulting in excess pressure diversion to this component, which is offsetting the connection. And in this case, the AI has picked up on a temperature-induced contraction due to a past weather event that has caused warping and leakage. Based off of this analysis and based off of the predictive capacity of this analysis, a cost-based, cost-normalized view of what needs to be done generates the following recommendations. We must repair the component that is causing the greatest level of loss, and we must induce a pressure reduction valve to essentially control for spikes in pressure that are increasing the level of loss, and where the types of events that lead to that type of pressure change are projected to increase 13.3% year over year due to the increasing nature of volatile climate events. We are also targeting speed of reduction and the speed of repair, which need to be reduced to no more than 3 days in this particular example. The actions we can take are governed by the models for prediction, which include speed of repair reduction, active leakage control, pressure management with pressure reduction valves, and infrastructure replacement. These recommendations allow us to focus on exactly those parts of the network that need the most urgent replacement or other type of repair or control, and where the cost of doing so mitigates loss at a level that is far in excess of what is required from an investment perspective. In other words, generating a positive return on investment. We welcome the chance to delve into other types of loss and how our system can help you in a follow-up demonstration. ITE is available as an SAP application on the SAP Store and can be sold through your relationship with your local SAP representative. Thank you for your time.